Can you see the screen now?
Yes, sir. Yes, sir.
Okay.
Visible, sir.
Okay. So today's my talk is Young's double-slit experiment. What's really happening at a single quantum level? Please let me know whether my audio is clear, my voice is clear or not.
Yes, sir. Yes, sir. Clear, sir.
Okay. So Young's double-slit experiment. What's really happening at a single quantum level? This is the talk actually. So all of you know that Young's double-slit experiment is a past 200 years before this experiment was designed by Young to demonstrate the wave nature of light. Before that, Newton's corpuscular theory was there actually, particle theory. And this experiment, we all know these things, but still this experiment is going on even in the quantum mechanics. Even today, some people will be doing this experiment actually. So that this, I think, no experiment has got that much popularity. But anyhow, let us recapitulate slightly from what we have seen yesterday. Talk. I have shown that this wave particle non-duality. This is the interpretation I am giving. This interpretation deals with a single objects actually. The Schrodinger wave function, the physical reality of the Schrodinger wave function is an instantaneous resonant spatial mode in which particles motion is confined. This is the whole idea. It is like a test particle moving in the curved space-time of general theory of relativity. It's identical actually. This can be proved mathematically using this quantum formalism I have shown yesterday. Another thing is that wave functions phase, overall global phase, when you solve the Schrodinger equation, unavoidably some phase is attached to the Schrodinger wave function. That will not appear when you take the inner product because it's a complex conjugate term. It will go away. So that phase is actually related to particular experimental outcome of an observable. This is the mystery of measurement problem actually. So using this, we derived the Bohn's rule as a limiting case of relative frequency of detection. And these things automatically solves the measurement problem actually. And this Bohn's rule I have given a geometrical interpretation also. This one. Okay. So that is what we have seen yesterday. And I also mentioned that there are many interpretations available. I have listed very few actually. From the mainstream Copenhagen interpretation to so many things are there. And 1 second, my screen is getting blocked. I will check how to do that. It's not going actually. Okay, fine. You can see the full screen without anything obstacle?
Yes, sir. Full screen is visible, sir.
Okay, then it's fine. I can go out. So this non-dualistic interpretation, you can derive a Bohn's rule using the quantum formalism. That is the main thing. That's what I have shown yesterday. And what are the salient features of this non-duality is that it gives the Bohn's rule as a relative frequency of detection. Measurement problem is solved. And another important thing is that this interpretation never takes anything extra from outside input action. It uses only quantum formalism and brings out the actual physical reality hidden within actually. That is the another important thing of this thing. And I also mentioned that there are many things we can, for example, this non-duality explains how Young's double-slit, what the mechanism have going on in the Young's double-slit experiment. Other things like well as delayed choice experiment, quantum eraser, etc. But now today I am going to talk about Young's double-slit experiment, mainly these two things. Before going to Young's double-slit experiment to explain this, I have to tell something little more actually, how this non-duality reproduces Copenhagen interpretation. This I have to explain, otherwise I cannot straightforwardly explain here actually. So first I'll concentrate on this one and then we'll see what is happening in the Young's double-slit experiment. So just as a recollect from the last talk, so we have seen this important thing is that this operator has a discrete eigenvalue. The spin SZ operator has a discrete eigenstates SZ up and SZ down with eigenvalues plus half and minus half. This is the operator with the discrete eigenvalues. In the case of discrete eigenvalues, we have to look at which eigenstate has the minimum phase with respect to the original aspect. This is the idea. right? Other vector, all other states will be having more than that value. And why you have to see this minimum phase? Because particle will be there only. This is the case of discrete eigenvalues. And in the case of continuous eigenvalues, this rule has to be little bit, we have to see that also. We'll see that little later. So remember this one, minimum phase only the particle will go. This is actually connected to the principle of least action actually. That why minimum, why not maximum? Null. Reason is because it's ultimately connected to the principle of least action. So just to recollect from yesterday's thing, and we'll let us see how to do with this. This is a two particle case actually. This one is a two states only there actually. Operator with the two eigenstates. You can generalize these two eigenstates, n eigenstate case or even infinite number of eigenstates. So consider this is for example, now I will see how to Copenhagen interpretation as a statistical average of non-dualistic interpretation actually. So the essence of Copenhagen interpretation, what actually we see in the textbooks are these two are the important things. The Copenhagen interpretation itself has many variants. There are no consensus among Copenhagen physicists themselves. They say people differ in so many ways, but ultimately these two things you can always see in their thing. These are the main things. So what actually it is, there is a quantum state vector expressed as a superposition of various eigenstates of an observable collapses to a particular eigenstate upon observation. This we have shown it for a two particle case. We have to generalize this for a n particle case, n states actually. So the probability for such a collapse is given by the Bohm rule. This is the essential essence of the Copenhagen interpretation. To see this one, what actually is take the observable A and its eigenstate. All eigenstates are AI, orthogonal eigenstates. So there are n number of them. So any state vector you can write in the space of A hat in this way. This is a well-known thing actually. These are the eigenstates of the A operator. So the particle enters into one of the eigenstates. One second. Bottom line I cannot read because this is blocking. I don't know what. Maybe I can move it up. Okay. So the particle enters into one of the eigenstates. Say this one. I am putting the index P to say that this is the state where particle is there. So this AP state, only one state has a minimum phase and particle will enter there, and we are labeling that state as AP, P for particle actually. Now upon observation, what actually I have already told, psi, its dual is excited in the detector screen and then interaction happens. So if you take this interaction, this is the one, but particle is there only in one state AP. So rest of all are there. They are all orthogonal eigenstates, but they are empty. So none of them will contribute. Only this will contribute. So this entire thing goes to here. Actually, this is the probable. This is actually, if you do repeated measurements on n number of states, n number of particles, this is actually equivalent to the Bohm probability. So if you sum over all these Bohm probabilities, it will be equal to 1 actually. This is the Bohm rule actually. So this is actually shows how these states collapses to a particular state. This is the Copenhagen collapse of the wave function advocated in the Copenhagen interpretation actually. So and then sum of all these probabilities actually one. This is the Bohm rule. These two are the Copenhagen interpretation's main points that actually we can show from the non-dualistic interpretation. So actually among why I listed again all the interpretation means, the reason is simply because this non-dualistic interpretation supports the Copenhagen interpretation. None of the other interpretations actually. It is consistent with the non-dualistic Copenhagen interpretation, but only statistically, because the Copenhagen interpretation cannot be applied to a single quantum behavior actually. So that is the thing. So let us move on to this. The last thing for a discrete operator with discrete eigenvalues. Now let us generalize it to operators with a continuous eigenvalues. A simple example for an operator with the continuous eigenvalues is the position operator. Its eigenvalues are just spatial points actually that spans the entire physical space, Euclidean space. So in that position operator basis, you can write down the state vector like this. Now the condition is this: earlier we had a minimum phase, particularly because they are all discrete. there will be one state which will have minimum phase. But here we have continuous basis actually. Therefore, there will be always one state whose phase will be exactly same as the phase of the state itself. So this is the difference between continuous basis and a discrete basis. There will be always a state. So actually what happens is that the particle naturally enters into that RP, that is position state actually. So now if you take the inner product, like in the case of a discrete case, what actually we have seen, only that state comes, particle will be found. Rest of the states are all will not contribute because it does not carry any particle in it. So now let us see this. This is the RFD, relative frequency of detection. Actually, if you compute, if you perform repeated measurements over a large number of particles, then if you sum over all these particle probabilities, you will get one. This is the Born rule actually. So this is the collapse of the wave function advocated in Copenhagen, because this is generalization of a discrete case, which is the same only. But the point is to show that non-duality can explain collapse of the wave function. So another thing is that we have this. We have made this thing actually. What is that? The phase of a state vector will be same as a particle state vector actually, because discrete continuous eigenbasis, there will be always one state with the whose space will exactly match the whatever is the phase of the state vector side. Using this criterion, we can actually derive these relations, the phase relations, as a function of time. It is initially the particle is at position eigenvalue x of p0, but at later time it will be at position eigenstate xp at t. So now actually this is the phase relations. Actually, this you have to derive. You have to, it is a little bit involved derivation. It's available in my profile actually. This is actually I did not write it down because aim is to do Young's double-slit experiment. But this you have to remember. You have to see the phase of the state vector is actually related like this. So this is the position state at the time t. You have this position state bases are evolving according to Heisenberg equations of motion actually. So this is the thing. From here, actually you can derive a least action principle of least action. What does this statement tells is that particle state eigenvalues. The particle state has its eigenvalue. That only the particle state eigenvalues always lie on a classical trajectory. That is the whole point. So even in the quantum mechanical case, a particle moves from A to B. One second. When a particle moves from A to B, this A to B is connected by a classical path. That path is filled with eigenvalues of the particle state actually. We can say it is exactly like classical mechanics, but there is a difference. This is not the relation in a Euclidean space, 3D Euclidean space, where actually you cannot say that xp and there are eigenvalues. You cannot say no. This is actually in the Schrodinger waveform. That is the space. So in that particle moves from A to B, and the eigenvalues lie on the classical path actually, particle state eigenvalues. This equation tells us that the time parameter entering in quantum mechanics is same as the time parameter entering in the classical mechanics. It's a very crucial, important result actually. And for example, this result is independent of whether it's a microscopic or macroscopic system also. This explains how microscopic quantum mechanical systems becomes a macroscopic classical systems, because simple reason. As the particle size is increasing, its de Broglie wave diminishes, means wave nature diminishes. But this is always there actually, either quantum or classical. You can always, this will be there. So macroscopic phenomena, you are not perceiving the wave nature very much. It approximates to Euclidean, but this result is there. This is we already know actually. So next thing, let us see how this result is important actually. Let me show you a video, little small video. This I have taken from Sean Carroll's video lecture. YouTube, it is available in YouTube. You can see. See, actually, what we have is that this is the radioactive element kept inside a bubble chamber, or it can be a cloud chamber, doesn't matter. So when the charged particles are emitted, they will come out like in straight lines. But according to Schrodinger's wave equation, if you solve the Schrodinger wave equation, the solutions are like a spherical waves. For example, a charged electron is emitted from the radioactive source. That wave function of the electron is a spherical wave. It is actually spreading in like a sphere. But that you won't see that in an experiment. Actually, what we see is a straight lines, like a free particle moving in a space. That's what we see. For example, let me show you. So that's how it is actually. So this result is not explained so far in quantum mechanical computing. I mean, this is the one thing which I can explain. Why it is because the wave function, Schrodinger wave function, of course, comes as a sphere, but the particles actually travels in a straight line because the free particle. This relation tells that those trajectories of the particles, they are all lie in a in a straight line path. So that is the thing I can actually show. That is the advantage. So these things are really needed. This much is needed. Let us go to the Young's double-slit experiment. Let us have a brief introduction. This is the famous quote by Feynman, Professor Feynman. He said that this double-slit experiment has the heart of quantum mechanics. It has the central mystery. It explains. It is about a wave particle duality. That's what actually they say. Because in the same experiment, we can see particles behaving like a waves, or particles behaving like particles and waves. Both natures you can see depending upon the experimental situation. So this wave nature of these things were proved for photons, electrons, neutrons, all those things exhibit this duality. Duality means what? It has both natures, particle and wave natures. So providing an explanation to this mystery classically, this is how to explain this classically means using classical intuition. How can we explain? Any attempt to explain this classically, it fails actually. The reason is, simple reason is this, according to non-duality, everybody tried to explain classically in Euclidean space. Their background space is Euclidean, and they are trying to explain why something is particle, why something, the same thing is like a wave at different situations. But the background space is Euclidean space, which is passive. It is playing a passive role actually. Like in the case of Newtonian mechanics, it's a passive stage. But in my case, actually, what actually happens is that is not the case actually. My case actually, complex vector space is the actual background field. Actually, what we have is the Schrodinger wave form as the spatial mode in which particles are moving. So automatically, this will explain now why interference and all those things happen. So let us see how non-duality explains the double-slit experiment. This is the diagram. Let me explain this one now. This is the source of light. For example, first let us consider as a light. We have a small opening through which some light comes. So this is the double-slit assembly. We have two slits here. Whatever the light going through these holes will come out this side, the rest is blocked. And we have a screen here. Here actually, according to non-duality, the inner product interaction happens actually. So let us see what is the known thing actually when a huge number of photons are coming, a stream of photons are coming. Actually, what you see is this interference pattern. Actually. Another thing, suppose now you dial down the intensity of the light source, very, very low intensity, means only one photon is emitted at a time. Next photon is not emitted before its detection at here. So means one photon is emitted, is detected here on the screen. After that only the next photon is fired. So you collect, then what actually happens? First photon comes and lands on the screen somewhere. The next photon comes and lands on the screen somewhere. And their arrival on the screen is very random. They will at different places, they will land. But if you collect a large number of those detected events, then they conform to this kind of a profile. They show interference actually. Now the thing is, single particle is always found as a single particle, but for a large number of particles, the overall profile is like this interference, which is in accordance with the Born rule actually. So what actually happens is the state vector here psi0, when it is actually this one actually projects out this state vector through psi1 and psi2, and these two are linear superposed, and that actually that's a square. That one here appears as the interference pattern. Suppose do another thing actually. Suppose you block one of these slits. Then actually what happens is particle will passes through only one slit. That time you will see this one. This one. For slit one, this is the shape you see actually. And suppose now block the upper one and open the lower one. Then you see this one. So our intuition tells us that if you open both of them, then the result should be sum of these two things. That never happens actually. This is because if it is phenomena is really happening in R3 Euclidean space, then if you add these two things, that's what should be the result of when both are open. But that's what not the case actually according to non-duality, because the particles are flying in the this Schrodinger waveforms actually. So when both are open, they will interfere. But in our Euclidean space, such things are not there. So when the straight vector is projected, these two things get linear superposed. And see, there are other things. For example, if you can have a detector actually, so both slits are open, but try to see through which slit the particle is actually going. When you switch on, you always find particle is going through this or this. It will never should tell you that a particle is going through both. Why I'm saying is that see, you are getting interference pattern even in the case of a single particle. If that is the case, means each particle knows that both slits are open. If both slits are open, how the particle is actually moving from here to here is a mystery actually. Whether the particle is dividing into half goes here, and they'll interfering. That kind of the ideas and all will come. But according to non-duality, there is no such thing. So wave function, when the moment particle comes in the source, from the source, the psi appears instantaneously everywhere. So it actually happens, these projections and this will pass through these superpositions and its inner product, everything happens actually at the moment particle is emitted. Now, what does it mean? Its space is already designed. How this is, space come into existence, the moment particle comes into the existence here, it appears. Then the particle simply moves either through slit 1 or slit 2, but this is moving in the Schrodinger wave field, you should remember, not in R3. Either through this or this, it will move, and if some places you have a dark wave function vanishes, it's there the particle will not go because its space is not available to that. So wherever it is there, it will go. Moreover, where it will land, it depends upon the phase of this wave function. Like in the case of a single particle case, discrete state I said, no, the phase is actual, decides where the particle is going to land. So depending upon the phase, this particle will land somewhere here. The next particle will come with a different phase to land somewhere. And these phases, so because of the nature of the source, these phases will not occur continuously, they are random. So the particle will arrive here randomly. But the point is, wherever the particle arrives, their inner product is same for all particles. So inner product is same means, even though they arrive randomly, if you collect a large number of them, you get this profile actually, this profile. Okay, that is the idea. So let us see. Suppose you try to find out through which thing it is going through. When the detector probe interacts with this particle, what actually happens is it is scattered into new state psi prime. In that case, actually earlier this psi had two origins, this and this as the two origins. The moment the detector probe interacts here, the earlier psi disappears and the new psi prime forms. That new psi prime will have origin only here actually. It will not have here. So you will see only one particle like nature actually. This only one thing it will form. If particle passes through this, this interacts with that, and again particle is scattered here. When it gets scattered, a new state appears, and that state actually has origin only at one place here. Earlier thing was moving through both. It has two origins. The moment it interacts, these two origins has disappeared, and only one origin it will have. This already I showed how the particles get scattered into the other state that I have already explained. So that's one you have to use here. Once you use that, you will see that the moment detectors are on, this is the thing you will see. If detectors are off, this is the interference pattern you will see. So all the features of Young's double slit experiment, we can explain using non-duality. I don't know whether I have put all the points. If you have any doubts regarding this, you can ask me at the end of this talk. I'm glad to explain. So this is the mathematical things regarding those things. For example, when psi interacts with the induced dual on the screen, this is what actually this is the interference pattern. And what you have, this is the phase equation I have written down earlier. This phase of psi decides where actually the particle is going to land. You have to see, if you look at, you can actually solve this one for the Young's double slit case. You can, different phases will make the particle to arrive on the screen, not at different locations actually. So that is the thing. Okay. So this is the same thing. Whatever I explained, I have written down here actually. So each particle, different particles with the different phases will arrive at different locations. But for all of them, interaction region is same. What is the interaction region? This psi, this is the interaction. This inner product is the interaction region for all the particles. Whatever is the phase, the global phase, it is disappearing because of this psi star. That it will cancel. But psi will make the particle to land on the screen at different places. So because of that, what actually happens is that if you collect all these points, it will actually use this function. Actually, it will actually, it's like a plotting, constructing this function using a small different points actually. So this is the thing. I think that is okay. That's about thing. This and all I explained. Suppose if you block the slit one, then you will see only one thing. This one, slit one is blocked. Then only through this, this is the one we can see on the screen. If slit 2 is blacked, this is the one you can see on the screen. If both are open, you will see the interference pattern. Okay, that's the thing. All these things I explained. This is about when the detectors are on. When the moment the detector probe interacts with the particle, the psi is scattered into psi prime, means near slit 1. Earlier, psi had two origins through slit 1 and slit 2. The moment it interacts, its origin becomes only one near that slit. So since one origin, it's like a spherical wave, and that profile when interference is lost. The same thing with the interaction at slit 2 also. Okay. So therefore, in the presence of detectors, clump patterns occurs, and in their absence, the interference pattern comes back. This is the quantum enigma. It can be easily explained by wave particle non-duality. That's about the thing, and these are the. There are different. I just give a simple reference. In this, I have all the papers at a place, so I am giving these sites. If you are interested, you can have a look at it. Thank you for your kind attention.